Hello, this is Marwan Omar, and today my talk will be on quantifying the performance of adversarial training on language models with distribution shifts. I'm an associate professor of cybersecurity with the Illinois Institute of Technology in Chicago, USA. Let's get started. So here's the outline of my talk. Introduction and motivation, and then we'll talk about related work. Then we will move on to talk about the methodology, and later on we'll talk about the results and evaluation, and we'll wrap up with a conclusion. Introduction and motivation. Deep neural networks or DNNs are vulnerable to adversarial attacks. Adversarial attacks are techniques to perturb the input data to force an NLP model to produce incorrect predictions. This is considered a fundamental weakness in the training algorithms for NLP models or large language models. Adversarial training, it leverages the gradient-based optimization technique to improve the robustness of language models, to make them more robust to future adversarial attacks or future adversarial examples. There are some shortcomings or weaknesses or limitations associated with adversarial training in the current literature for the NLP. Researchers consider a static view of models, meaning they think that language models, once deployed, they do not change. However, as you know, language models have to adapt to the changing needs of the production environment. So models shift and drift and are subject to distribution variations. This means that models are likely to encounter data that are different than the data they were trained on. This means that we have to reevaluate NLP models even after deployment to production systems, because failure to reevaluate NLP models after adversarial training for long-term effectiveness will be an issue. So that's one of the limitations of the current literature on adversarial training in the NLP domain, is that NLP models are not being reevaluated after adversarial training. So this is an important aspect that we need to keep in mind after conducting adversarial training. Although adversarial training is effective for the short term, it may not be as effective in the long term, once again, because these language models will encounter and experience data points that might differ from the data points that they were trained on, which means that there's going to be a distribution shift. So the training data the new data will not have the same distribution as the training data. Quantify the performance of adversarial training. Adversarial examples are distribution dependent, limited due to distribution shift in the underlying data. Once again, even though we train our models with adversarial examples, this adversarial example training may not remain effective for the long term due to distribution shift. The task that we are discussing here is a sentiment analysis task for language model, which is a very popular task, a very popular linguistic task. We validate the shortcoming of adversarial examples and adversarial training on this sentiment analysis task. Adversarial training degradation. Degradation in the performance of adversarial training is both data set and learning technique dependent. This means that depending on the technique that we use for adversarial training and depending on the data set, if we use a data set from the sentiment analysis task, we might get different results than using a data set from a different task like malware analysis, malware classification, or another linguistic task such as question answering or natural language inference or topic classification, for example. We can talk about the related work in this section. Once again, adversarial examples or adversarial attacks have been studied extensively in the literature. So adversarial attacks are purposeful attacks designed to fool or mislead NLP models. They work by perturbing or modifying the input data or the input text and fooling NLP models in producing incorrect predictions. They are used to test the performance and accuracy of NLP models. Here is an example. The original example here is perfect performance by the actor. An NLP classifier will classify this with 99% confidence as a positive sentiment. These are customer reviews as part of the sentiment analysis task. If we just replace the word perfect with the word spotless, this will lead to a different prediction by the NLP model. So if we say spotless performance by the actor, the NLP model will say that this is a negative sentiment with 100% confidence. We know as humans that this is actually a positive sentiment because the customer is basically praising the actor. So an adversarial example generated using Gia et al. 2020 text fooler. Text fooler is an attack technique that allows us to generate adversarial examples in order to evaluate the performance and the accuracy of our language models using the BERT sentiment classifier. So here, again, swapping out perfect with the synonym spotless completely changes the model's prediction. Even though the underlying meaning of the text has not changed, the semantics have not changed, the meaning has not changed, but the prediction by the classifier has changed, which is an issue that we would like to address. Adversarial training as a defense mechanism. AT or adversarial training in the vision domain, originally pioneered by Goodfellow 2015 to address adversarial attacks. In Goodfellow is one of the first researchers in the domain, in the vision domain, who introduced or coined adversarial training. Models are more robust against real-world attacks after adversarial training, again in the short term. Adversarial training in the NLP domain is considered the de facto standard to achieve robustness to adversarial attacks. How do we generate adversarial examples? There are many works in the literature that discuss how to generate these adversarial examples using attack techniques. They focus mostly on a binary classifier for spam detection using spam ham dataset and some other sentiment analysis tasks. In this section, we are going to talk about the methodology. Here is our experimentation pipeline. We start with a pre-trained model exposed to adversarial examples. Then adversarial training is conducted to cope with those adversarial examples. So we have the pre-trained model. Then we generate adversarial examples. Once we generate adversarial examples, we test our model with these adversarial examples, and there is a high misclassification rate. So the attack success rate, in other words, is high because this classifier does not have any defense. We haven't trained this classifier on adversarial examples yet. We're just attacking it to test the performance, to evaluate the accuracy. Then afterwards, we incorporate these adversarial examples as part of the adversarial training into our language model retraining. And we test them again, we see that the misclassification is low, which means that the attack success rate is low due to adversarial training. However, there's something called a concept drift, which means that models shift and drift when they experience new data sets from the real world after deployment to the production environment. So then, if a model experiences adversarial attacks again later on, while after being deployed to the real world, then the misclassification rate goes up again, which means the attack success rate is high. So this is a shortcoming of the adversarial examples. Sentiment analysis task. We define X as an instance of the input text and Y to be the target label of the sentiment. The sentiment classification task is denoted as a mapping function X leads to R. Various model architectures have been used in this experiment. So we experimented with BERT, which is a transformer-based architecture, or CNN, convolutional neural network architecture, and LSTM for long short-term memory, which is a different type of architecture. So we use different types of architecture to determine the effectiveness of adversarial training when we change the architecture of the model and also the data set. Adversarial examples, again, are inputs designed to attack and fool an NLP system. More specifically, an adversarial example is defined as an input X obtained by solving an optimization problem. So we treat adversarial examples generation as an optimization problem. Adversarial training improves robustness by integrating adversarial examples into the process of training of the model. We optimize the loss function to minimize the computational cost associated with creating adversarial examples. We modify the training objective by applying a small perturbation to the input text that maximizes the adversarial loss, as in the following equation. So we have our cost function, which is also called a loss under distribution of samples, and we write down the risk function as in the notation. Here is our implementation details. We utilize the projected gradient descent, PGD, which is a powerful and popular optimization algorithm for machine learning in general. We implemented the algorithm using the text attack framework to test adversarial examples that we generate. Text attack is a popular framework for NLP research to generate adversarial examples so that we can evaluate the performance of our language model. Distribution shifts, we assume the static data set, limiting the impact of the adversarial training to the current data and making the adversarial example less relevant to other data sets. The underlying model will be constantly exposed to new data, so distribution of the data will change over time. As we had mentioned, we shouldn't expect the models after deployment to production environments to experience the exact same data or similar data to the training data. We expect models to experience data that they have not seen before. And that's where the distribution shift might happen. When that happens, the model performance could degrade, meaning that if these models experience adversarial attacks in the near future, then they are more likely to be fooled again by these adversarial examples, which means that these models will produce incorrect predictions, and that's something that we want to address. Results and discussion. Data sets, algorithms, and metrics we use in our experimentations. This is the table with the data sets IMDb, movie review, and Yelp for our sentiment analysis test. So we utilize 3 different data sets: IMDb, movie review, or MR, and Yelp. These are 3 popular benchmark data sets in the sentiment analysis task. Each data set has binarized ratings and is set as positive or negative and split into training and test. So IMDb is a large movie review data set, a set of 25,000 data points for training, another 25,000 for testing. The MR is the movie review data set of 5,331 for training, another 5,331 for testing. And finally, our Yelp data set, which is the large Yelp review data set, has a set of 560,000 data points for training and 38,000 data points for testing. Data sets again. So once again, we used BERT for CNN and LSTM. The evaluation metrics are the accuracy, which is the number of correct sentiment predictions made by the model normalized by the total number of predictions. Then the misclassification rate, which is the total number of the wrong predictions made by the model normalized by the number of predictions. So these are the two metrics we use to evaluate the results, the accuracy and the misclassification rate. Here are our results. Baseline experiment shows the classification accuracy of each of the three models prior to adversarial training. We know that BERT consistently achieves the highest classification accuracy. Conversely, CNN consistently achieves the lowest classification accuracy. So we have BERT on the IMDb with an accuracy of 90.01. On the other side, we have CNN with 86.32 classification. So CNN performs better than BERT. BERT is the top performer. And here are some more results. So this is a table for the misclassification under adversarial examples. The misclassification rate increased after introducing the adversarial examples. We observe that BERT again is consistently performing better than the other models across multiple data sets. And the retraining with adversarial examples, the encoder and decoder for generating adversarial examples. So you use the encoder-decoder architecture. Adversarial examples adhere to the linguistic constraints and preserve semantics. So in this table, adversarial training results, note that the accuracy rate after the training for each model consistently increased across multiple data sets. After adversarial training, the accuracy increased. And then after the retraining, the misclassification rate here, we validate the temporal changes and prove transferability of the results. The misclassification rate with the retraining upon adversarial training, note that the retraining models of the models with adversarial training examples yields a lower misclassification rate. Here is the conclusion. Adversarial training performance, the impact, we studied the impact of adversarial training, and we noticed that adversarial training impact fades away over time after serving new data. We also noticed that transform-based models suffer performance degradation to a lesser degree relatively. CNN-based models suffer performance degradation to a higher degree relatively, and LSTM models significantly degrade in their performance. Thank you for the time and attention. This is the end of the talk.